Today we are talking about finite and infinite decimals, ADM 7, lesson 6. And like many of these lessons, the title isn't exactly what the lesson nor the homework is teaching. In this case, we are learning how to convert fractions into decimals in a method other than using long division, in addition to also being able to look at a decimal or a fraction and immediately being able to tell, or very quickly being able to tell, whether it's going to terminate or repeat forever. So that's kind of the overview. We're going to spend 20 minutes learning about what I'm talking about. And so let's get right to it. We're going to start with kind of an overview of really something that you kind of may have learned already in in 6th grade or 7th grade. And that is point number one. If a number can be written as a fraction, so what am I talking about? Let me just draw some examples so that you're not totally in the weeds on this one, or in the forest, or totally confused. So if a number can be written as a fraction, so here's some numbers that can be written as fractions. You know, these are all fractions. It will either terminate or repeat when written as a decimal. Okay, so when you convert these to decimals, they will stop, they will terminate or repeat. So what is a terminating decimal? These are decimals that stop. So 0.5, it stops because it stops here at 5. There's no more decimals after this. 2.25, it has an extra decimal place, but it stops. It doesn't keep going. 6.3 is also terminating. Also terminating would be like, the number 7. That terminates. It doesn't have any decimals. So these are all terminating decimals. So what's a non-terminating decimal? Well, there's actually two kinds. One is a repeating decimal, and these are ones that never stop. They go on forever, but they start a repeating pattern at some point. So like 3.33333333333, that's going to go on forever, and that's what these ... represents. But it repeats this pattern of threes. In some cases, you also have repeating patterns where the repeating pattern isn't just one number, but it's more than one number, like 0.090909090909. Or it could repeat 3 numbers or 4 numbers or 5 or even 10 numbers. But if the numbers keep coming back over and over, that's a repeating decimal. So these repeating decimals can also be written using what they call bar notation, and this should be familiar to you. So that this number of 3.33333, you don't have to write so many decimals and then these dots. You can just write that as 3.3 with a bar over this 3, and that means to repeat forever the thing under the bar. And in this case, this 1.0909090909, you don't have to write it, this long. Instead, you could just write it 1.09 with a bar, and that means to repeat forever the 0 and the 9, like this: 0, 9, 0, 9, 0, 9, 0, 9, ... But we don't have to write all that green stuff. We can just leave it here with this blue stuff and the bar. Okay, so that should all be familiar to you. There's one other kind of decimal that we're not going to really talk about today, but that would be a decimal that repeats forever, but keeps going on forever, goes on forever, and never repeats. So that's a possibility. That's a number like pi. So 3.1415962 ... and it never repeats in a predictable fashion. It may repeat some numbers. Somewhere in this long string, you may get a 3, 3, 3, but then it would go on like 2, 1, 4, 6. It never hits a pattern that keeps on going forever. And there's mathematicians that have proved this. we're not going to bother proving that there are such numbers, but there are many such numbers. Okay, so let's just carry on rather than delve into that concept of numbers that go on forever but never repeat. So this is also kind of review from maybe year 6 and year 7, grade 6 and 7, where you can turn these fractions into decimals using long division. And you know how to do this. So let's not worry about this point over here. We'll get to that in a second. The first thing I want to do is just remind you how to do long division. And for those of you who forget whether this looks like, you say, if you ever figured, does that go like this or like this? Which one is the right way to write this? And the way I like to remember it is box top. You know, box top. That's a saying that some of you have heard before. It's like the top of your box that you rip off, and they sometimes have coupons on it, but box top. So the number on the top goes inside the box. So this 3 is on top, so it goes in the box. All right, so it goes in the box. So the 8 goes on the outside. We remember that? So hopefully this is something that works for my students that I taught in the classroom for a while, where they never screwed this up after they remembered, hey, box top. Okay, so now we put 8 into 3, and so you know how to do long division, so I'm not going to harp on this one, but I'm just going to do it. I'm going to do the work for you, and then we'll be done. So that's 0. So that's how you convert a number using long division. You just do the long division, and then at some point it will maybe terminate. And let's try this other one, 8 over 9. So what goes in the box? Box top. 8 goes in the box. So let's do this one. Here, let's do this one in a different color so that you don't get too confused. So we'll go 8 goes in the box, and then 9 goes outside the box. So 9 goes into 8. Let's see, that's 7 times. That's 63. Wait a minute. 8 goes, that's 8 times. 8 times. Mr. Lipscomb, wait, let's just undo this. 8 times. I knew something was screwed up there. So that's now 8. 80. 8 times 9, 72. And now that we have gotten a number that repeats, if this number repeats here, now we know that we have a repeating pattern. And we can also see it right up here. So this is 0.88888888. So that can be written as 0.8 with a bar over it. Now, the first new learning, and perhaps it's new for you, it's not new and that you've already learned this, but a trick to know if a fraction will terminate when it's written as a decimal. Now notice that this one terminates, and this one repeats forever. Now, the key is, if the prime factorization of the denominator is only 2's and 5's, it will terminate. Otherwise, it will repeat forever. So that's this point. If the prime factorization of the denominator contains only 2's and 5's, it will terminate. Otherwise, it will repeat forever. This isn't something we're going to prove, but you're going to get an intuitive understanding of this by the time this lesson is over. So let's see. So we know that this should terminate because we're going to do a prime factorization of this 8. So if we take a prime factorization of 8, we get 4 and 2, and then 2 and 2. So 8 is equal to 2 to the 3rd. So this prime factorization of 8 contains only 2's. If it also had 5's, that would be okay. And so we know it will terminate. And we'll get into why in a little bit. So we look at the denominator. It has only twos and fives, so it will terminate. Now let's look at this, and we know that this will not terminate because when we take 9 and we do a prime factorization, we have these 3's. And so because the factorization, the prime factorization, has numbers other than 2 and 5, it will repeat forever. Okay? So this is the rule, and we're going to use this as we build on finding another method for converting fractions that terminate into decimals. And that's a lot of what this lesson is about. It's about identifying numbers, identifying fractions that will terminate, and identifying fractions that will repeat forever. So the question is will these terminate or repeat forever? And so the first thing we're going to do is we're going to guess if we're going to determine if they repeat or terminate. And then B, find the value. So we can just find the value using long division, but we're going to predict in advance for fun to prove our point. Okay, so the first thing we're going to do to determine if they repeat, we're going to do a prime factorization on our 25. So our 25 is a 5 and a 5. So because it has only 2's and 5's, it will terminate. We know this will terminate. And so let's prove that. Box top. Our 2 goes in the box. Okay. So let's put this down. So 25 doesn't go into 2. That's a 0, 25. Well, let's see, that's wrong. So it doesn't go in 20, so it's going to go in 200. So there we go, 2.08. 8 times 25 is 200. There we get 0. So our answer is 0.08. So it terminates. We did the right thing. Okay, let's try 5/12. So the first thing we're going to do is we're going to take our 12 and we're going to prime factor it. Well, I don't know if is the right thing to say, but it has a 3. So this will repeat forever. Because we don't just have 2's and 5's. We also have this 3. So it will repeat forever. It has a number that is not a 2 or a 5 in the prime factorization. So let's prove that. Okay, box top. 5 goes in the box. So 0, that's a 4. 4 times 12 is 48. 2, 0. 12 goes into 20 one time. 1 times 12 is 12. 8, bring down our 0. 12 goes into 80. Let's see, 6 times. 6 times. 6 times 12 is 70. Whoops, what did I do there? 72, and that's 80. Okay, so we have a repeat, 80 to 80. So we know that we now have a repeating pattern. So we get 0.416 with a bar over it, which is good. It repeats forever, as we predicted. Isn't this cool how this neat little trick works? I find this totally cool. So now, let's see, 3 over 16. Let's take our 16 and let's do a prime factor. Okay, this is cool. It only has 2's and, well, there's no 5's, but it only has 2's. So this will terminate. Okay, so box top, so we put our 3 in the box, and our 16 over here, point, 0. So that's a 1, 16. Uh-oh. This is a mess. 14. 140. 16 goes into, let's see, that's 8 times. 8 times 16 is 128. 12. Bring down our other 0. And we get 7. 7 times 16 is, let's see, 7 times 16 is 112. That's 80. And we get 5. That comes in 5. 5 times 16 is 80. And we get 0. So our answer is 0.1875. We had to do some division. We had to do a lot of division and multiplying, but we figured out that this does finally terminate, as we predicted from our prime factorization. And I'll just run through these last ones a little bit more quickly. So 2 over 50, here's one where we have 50, and we get 25 times 2, 5 times 5. So this only has 5's and 2's in it. So we predict this will terminate. Box top, 2, 50, point, 0, 0, 0, 0. So that goes in 4 times. 4 times 50 is 200, 0. So our answer is 0.04. So that did correctly terminate. This is so cool how this works. And you know what I forgot to do here? We got to lay down our happy cats. Happy cat, happy cat, happy cat, happy cat. And now let's do our last one here. 18 is 9, 2, 3, and 3. So because there's a 3 in here, this will repeat forever. It will not terminate. It will repeat forever. So let's see. Let's put our 1 inside our box top. And our 18 here, point, 0, 0, 0. Okay, that goes in 5 times. 5 times 18 is 90. So we have 10. Sorry, so we pull down. We have our 100. 100 goes in 5 times. 5 is 90. And then we have our 10. So we have our 90 repeating here. And so we get, we'll have 0.55555 or 0.05 with a bar over it. So we correctly predicted it will repeat forever. So we have this cool trick, right? We know how to do our, we do our denominator and we do our prime factorization, and then we can figure out whether or not we terminate or not. So that's point number 1. Now, point number 2 is this. This is actually the meat of the lesson. We're already a little ways into the lesson, but this is the meat of the lesson. And you are going to be able to find decimal values for terminating decimals not using long division. So for terminating decimals, so for fractions that are terminating to decimals, you are going to convert not using long division. And this is pretty cool. So our goal, and we're going to do a lot of examples of this. So this is just the explanation, but we're going to see how it works on future slides. We're going to convert the fraction into one that has a power of 10 on the bottom, which is the denominator. And then we're going to be able to find our answer without ever doing any division, just multiplication. This is so cool. So these are our 4 steps. And these are kind of long, but I'm going to shorthand them for you on the next slide so that you'll be able to remember maybe a little easier. So we're going to factor the denominator into prime factors, and we're going to write them as a power of 2s and 4s. So for example, in 1 over 4, we're going to do a prime factorization, which is 2 times 2. And so we're going to write this as 1 over 2 squared. Okay, that's step 1. Step number 2 is we're going to figure out how many 2s or 5s you are short so that you're going to have the same number of 2s and 5s. This will create a factor of 10 on the bottom. Okay, so in this case, we have 1 over 2 squared. So we have 2 2s. We need 2 5s to match those 2 2s. So we're going to, what we're missing 2 5s. So we're going to write over here 2 5s, like 5 squared. Okay? Then we're going to multiply the top and bottom by this 5 squared. So we have 1 over 2 squared. And we're going to multiply it by this special value of 1, which is 5 squared over 5 squared, which doesn't change the value. And that's going to be 5 squared over 2 squared times 5 squared. And that's the same thing as 5 squared over, and this is 2 times 2 times 5 times 5. But we can rewrite that as 2 times 5 times 2 times 5, right? Because that's 2 2s and 2 5s multiplied together, and we just rearrange them like this. Now look what happens. We get 5 squared over 10 times 10, which is equal to 25 over 100. Now we have this cool fraction that is so easy for us to convert into a decimal. So 25 over 100 is equal to 25 with the decimal moved 2 times. That's our division trick that we learned in 7th grade. So that's equal to 0.25. And look, no hands. We converted 1/4 into 0.25 with no division, just multiplication. Very cool. So let's do that again. Uh-oh, our example is 1/4, and we just did 1/4. So instead, let's do 1/5. Let's do 1 over 25. Okay, we'll do that one. So let's do it in green. Okay, so we're going to factor. Here's the shortcut. Factor, calculate the missing factors, multiply by top and bottom by the thing in B, and then we're going to move the decimal. Okay, so let's do that. So A is factor, so that's 1 over 5 squared. And remember, this only works, it only works for terminating decimals. Only works for terminating decimals. And we know this is terminating because it's only comprised of 5s and 2s. So that's the first thing, factor. Now we're going to calculate the missing factors. And so the missing factors are, we have 2 5s, so we need 2 2s. And that's going to make it so that we have the same number of 5s and 2s. Now step C is to multiply both sides, or the top and bottom, by our missing factor. Okay, so now we have, on top, we have 2 squared, and on the bottom, we have 2 squared times 5 squared. And on the bottom, we can rewrite this as 2 times 5 times 2 times 5. That's just using our expanding our numbers, or expanding our powers, and then using commutativity and associativity to rewrite it like this. And on top we have a 4. And so that's equal to 4 over 10 times 10 over, which is 100. So now in step D, we just rewrite this as 4, but we have to move it 2 decimal places for our 2 zeros. So we take our decimal and we go 1, 2, and put it right here. So we get 0.04. All right, let's do it for 1 over 20. This is going to be a little bit different because when we do a prime factorization on 1 over 20, we get 1 over, let's do this as, yeah, I'll leave it as 1 over 20. So, or how about let's do this as 7 over, how about 11 over 20? Let's just do it to change it up just a bit and put another number on top. So now we have 11 over 20, which is if we do 20, we get 4, 5, 2, 2, and 2. So that's 2 squared times 5 to the first. We'll just write that first right there. So we're short. What are we short? We're short only 1 5 this time. So we're short 5 to the first power. So now we're going to multiply top and bottom. Times 5 to the first over 5 to the first. And that equals 11 times 5 over 2 squared times 5 squared. So that's equal to 55. And I'm just going to do this in my head now because I know that this is going to be a 1 with 2 zeros after it. Just look at it. Because I can rewrite that as 2 times 5 times 2 times 5, which is equal to 100. If you want to go the long route, which is still fine, you can write 2 times 5 times 2 times 5, which is 10 times 10. But know that whenever you do this, you're going to end up, whenever you do anything like, if 2 to the first times 5 to the first is 1 with 1 zero after it. 2 squared times 5 squared is equal to 1 with 2 zeros after it. 2 cubed, 2 to the third, times 5 to the third is equal to 1 with 3 zeros after it. So 2 to the fifth times 5 to the fifth is going to equal 1 with 5 zeros after it. So you'll see that pattern. I've been doing math a long time, so I recognize this pattern. It's okay for you if you write it out, you know, the longhand. But here we go. We have 55 divided by 100. So in step D, we say, well, that's 55. And we have 100, so we have to go twice over. So that's 0.55, and we always stick our 0 out front. Now it's your turn to do some of this math, and this is our homework help and our final screen. And our final screen has you doing 5 problems. So I want you to pause and try and do these examples. Okay, now I assume you're back. So we'll do our examples, and we'll do this first one in green. So step A, we're going to factor this guy. So we get 3 over 2 cubed. Our missing number is, now we have 3 2s, so we need to multiply top and bottom by 5/3. So then we say 3 over 2 cubed times 5/3 over 5/3. So that's equal to 3 times 125 on top. And on the bottom, we get 10 times 10 times 10, which is, right? This is 2 times 5 times 2 times 5 times 2 times 5. There's all our factors. 2 times 5, 2 times 5, and 2 times 5. So on the top, if you do this multiplication, you get 375. And on the bottom, you get 1,000. So we're going to have to move the decimal 3 times up here. So we have 375, 1, 2, 3, and we get 0.375. 2 over 25, so here we get 2 over 5 squared. So we're going to multiply by our 5 squared. Nope, sorry. What's missing? A 2 squared is what's missing. Let's just write the whole thing out. What's missing is our 2 squared. And so we're going to say 2 over 5 squared times 2 squared over 2 squared equals, well, 2 times 2 squared is 2 times 4 over 2 squared times 5 squared. So that's equal to 8 over 100, which is equal to 8. We got to move the decimal twice. So we have to put our zeros out front and move our decimal once, twice, and we get 0.08. 7 over 20 is equal to 7 over 2 squared times 5. Our missing number is 5 over 1. So 7 over 2 squared times 5 to the first times 5 to the first over 5 to the first equals 35 over 100. Did the shortcut there. And so that's equal to 0.35. We're going to move the decimal twice on our 35. And you know what? Let's just lay down our happy cat. Time for a little break and enjoy our successes. Sideways happy cat, spinning happy cats and such. Okay, 3 over 50. Let's switch colors just because we can. 3 over 50 is equal to 3 over 2 times 5 squared. Our missing number is 2 to the first. So we got 3 over 2 to the first times 5 squared times 2 to the first over 2 to the first. So that's equal to 6 over 100. So that's equal to 0.06. Remember, you have to move that decimal twice because it's 100. So if you have a 6 here, you have to go once, and you have to go one more time. So we have to put our 0 here and go one more time. Boom. 0.06. And now, oh, this is a hard one. So let's do our factoring on 1250. I'm doing this one because you got one like it on the homework. So 1250 is the same thing as 125 times 10. 10 is 2 times 5, and 125 is 25 times 5, which is 5 times 5. So here we have 1, 2, 3, 4 5s and 1, 2. So this is equal to, let's do this in another color because I can imagine it's running into something else. So here we go, 3 over 2 to the first times 5 to the fourth. So here we're missing 3 2's. So we're missing 3 2's, and that will give us 4 5's and 4 2's. So let's take our 3 times 2 to the first times 5 to the fourth and multiply top and bottom by 2 cubed. So on top, we got 3 times 8. And on the bottom, we have 2 cubed times, 2 to the fourth. 2 cubed times 2 to the first is 2 to the fourth times 5 to the fourth. And so we have 1 with 4 zeros after it on the bottom. 1, there's our 4 zeros. So if you need to do this out, you could say, well, there's 4 2's and 4 5's, so that's 2 times 5 times 2 times 5 times 2 times 5 times 2 times 5, which is 10 times 10 times 10 times 10, which is equal to 1 with 4 zeros after it. There we go. So we got 24 over 10,000. So now we have to take our 24 and we have to move our decimal 4 times. So I'm going to write my 24 down here, and I'm going to put a few extra zeros out here, and we're going to move that decimal 4 times. This is totally critical. You've done all this hard work. You want to make sure you don't screw this up. 1, 2, 3, 4. So the decimal goes right here. 1, 2, 3, 4. So our answer is 0.0024. And I'm just going to do that on my calculator to make sure I didn't do anything wrong. And indeed, we have a happy cat. We have a happy cat because he loves it. He purrs when the math is right. So there you have it. A new method, perhaps for you, for learning how to convert finite decimals, which is another word. I didn't even explain this. Finite decimals are decimals that terminate, and infinite decimals are ones that go on forever. But how to turn fractions that we know are finite or terminate into decimals without doing any long division. It is so cool how this works. So hopefully you enjoyed it too. And we'll be back to 8M7, lesson 7 next time on Happy Cat, Happy Math.